Hey everybody, today we have a version of a 2009 competition problem. And y'all, monic, by monic we mean the leading coefficient is equal to 1 for any polynomial. So a monic quadratic has a 1, just like the given one here. With the given information, there's an understood 1 there. Q of x is also a monic with roots a plus 1, b plus 1. Notice this one has roots a and b. Now this one relies on a result called Vietas, and it's something you can discover on your own without memorizing the formula. But for every 0, there's a factor, right? So if a is a 0, x minus a is a factor. If b is a 0 or a root, x minus b is a factor. Now when you expand this out, you get x squared minus a plus b. And minus a plus b is the coefficient of x. So it's the negative sum of the roots that present as the coefficient of x. And then of course finally these two minus signs cancel, and so you just have plus ab right here. Okay. So that's the product present as the constant term, and minus a plus b is the coefficient of x, which is the sum of the negative roots, okay? So the goal is to find the sum of the coefficients of q of x, okay? So let's go down. Now this is what I just said a moment ago. This m would equate to minus a plus b, right? This m right here equates to minus a plus b. And also AB itself comes back to minus 1348, right? So that's just what we call Vieta's results, an Italian name, I think, for this first one. Now let's relate this to the second polynomial, q of x. Now using the same sort of reasoning, just like minus a plus b present right here is the coefficient of x, it's the very same thing right here, except it's a plus 1 and b plus 1 that are the roots, all right? And it looks like I left out an x right here. There should be an x right there, okay? All right, now what are we supposed to do? We're supposed to sum. All you're supposed to do is sum the coefficients. And again, y'all, you see how I just doubled down on, think of a plus 1 being here and b plus 1 being here. This is what would happen, okay? Now, so we're supposed to sum up these coefficients, okay? So what do we have? We have 1. Now, y'all, this looks like, what do we have here? Minus a minus b. And y'all, all I'm trying to do is sum the coefficients, not the x's, of course. All right. And then right here you have 1 plus 1, but there's a minus in front, so this would be minus 2, right? Okay, now when we expand out the constant term, we get AB okay, then plus A plus B plus 1. But look what happened. We have 1 plus 1 from here and here, the minus 2, and also the AB's cancel out. So notice that this is just equal to AB. Mass cancellation, all that survives is the cross term AB. But recall from the very beginning here, AB is just equal to minus 1348, all right? So that's the sum of the coefficients is the constant term of the first polynomial, which is kind of interesting. It's not surprising once you see the algebra, but you wouldn't anticipate that a priori. All right, so we got that. All right, so that's the answer to the question. The sum of this is the sum of the coefficients, right? So I'll just write out here, this is the sum and I'll abbreviate coefficient, just we'll call it COEF. Some of the coefficients, okay? Now, so we're done with the problem, but let's work with another concrete question or example just to show you how this works out all the time. Let's say we had the polynomial x minus 5 times, let's say x plus 8. Okay. Now, high school algebra indicates this would be a squared plus 3x minus 40, right? Okay. But what do we do now? We increment each of these zeros or each of these roots. So if you increment 5, you get 6. So we would have x plus 6 here. Right? Now notice right here, negative 8 is the root. So if you increment negative 8, you get negative 7. If you add 1 to negative 8, you get negative 7. So notice what happens right here, folks. You get right? Okay. Now, so what happens here when you expand this out? You get x squared, what, minus 2x plus, let's see here, oh, no, we get x squared plus 13x. I'm sorry, y'all, this is a minus sign right here, my bad. This is a minus sign, okay? So what do we end up with? We end up with, this would just be minus x here, right? And then, and so we have minus 42 here, okay? Like this. And this is a plus x right here, right? Okay. Now notice though, when you add up the coefficients here, you have a 1 here and a 1 here. So you have 1 plus 1 minus 42 is equal to negative 40. Voila. See, it's the same thing. When you sum the coefficients, here, you get the very same thing as the constant term in the original polynomial. So that's seeing is believing. This is theoretical proof right here, but this is a concrete example. Okay. So we've shown basically, I think the guy who composed the problem, this is all independent of whatever m is equal to. Notice how m, we never even used it. Okay, m is just an arbitrary constant actually for this particular problem. So anyway, well, maybe not quite. You have to look at, but we didn't actually use m in any sort of way as far as this proof. Okay, so what do we get right here? So we got minus 1348. So the sum of the coefficients right here is minus 1348. Identical to the constant term. Right up here. Okay. Talk to you later.